All right, so thank you. So today I would like to try to explain a bit better this entanglement memory theory. And then in the time that remains, I would like to introduce this class of dual unitary circuits. So there's not a lot of time left, so I will perhaps just introduce them and mention a few results. And of course, if you're interested, we can discuss this maybe at a discussion session or later, or you can also email me. So the entanglement membrane theory, you can find a somewhat self-contained reference in this paper. Though here, again, they don't put a lot of effort into try to make this rigorous. And okay, so I will try my best to now clarify what I failed to explain last time. Okay, so the idea is we start from the exact calculation we did at the level of dual unitary circuits. Yeah. Membrane. So this is entanglement, this is membrane. And this is theory. Membrane, because when you generalize to higher dimension, you don't have lines, you have membranes, yeah. Okay, so now from the lattice, say, calculation, we had this exact expression, sum over domain walls. And now here I will draw some pictures. Okay, so we literally had to sum over all microscopic domain walls, separating some region A from the rest. And here we are assuming that this is a quench and this is an entangled initial state. So we took, for example. Okay. So now we take large space-time scales. So without defining formally the scaling limit, you can whatever I will say next apply. I mean, you can think of taking system sizes which are very large and times which are very large. Right. So now we coarse grain this picture, and now let me first take a coarse grain snapshot of that and introduce some quantities before moving on. Okay. So now here we have our A. So if we zoom out, then microscopic domain walls will be replaced by curves. So this is time. This is space. Okay, so this is a two-dimensional vector which we parameterize with time, and the first coordinate is this one. And then whenever we have this type of curve for a given time t, we associate to this a velocity, which is nothing but the derivative with respect to time. Yeah, so this is a number because we're taking the first coordinate and we're taking the derivative with respect to time. Okay, so the idea is that now whenever we have this kind of microscopic domain wall, we do not sum over these microscopic domain walls, but we sum over macroscopic curves. And so we go from sum to path integrals, and then as it's really standard in this case, we associate to each macroscopic curve some entropic factor. So the way to think about this is that whenever you have a curve and you want to interpret this as a microscopic curve, there are many ways in which you can do this. Because microscopically, this will have many oscillations, and there are many microscopic ways in which this can oscillate to reproduce the same coarse grain curve. Yeah, please.
In the lattice calculation, it was obvious that we always add one curve, I mean one single Dunbar's curve. But here, if it's, we suppose that this is a monovariated functions of time. I mean that we do not have.
Yes. So this would be. You mean that this curve cannot do, something like horizontal. I mean, so we will see, in a sense, it can go up, right? Because we expect that something like this is allowed. So maybe, I mean, you say you want to give some constraint to this curve that maybe doesn't do something crazy like this. Yeah, no, but this will come out of the theory. So for the moment, let's not worry about this. Yeah, okay. Okay, so now I go from here to the path integral sum. So I'll call this star. Okay, so yes, also in the following, I will take the log of this. And for this particular case, the log of this expectation value, we said it's numerically very close to the expectation value of the log, so it will be a bit sloppy. I mean, last time we introduced, so we defined this to be the minus log of the expectation value. But then we said that for our particular problem, I'm just recalling this fact that we used. So usually the entanglement membrane theory is supposed to be a theory describing this quantity, which is the physically relevant quantity, so the expectation value of the log, the average entanglement. Here, this discussion is at the level of this quantity, but for the moment, I mean, in this discussion, we will not worry about the difference. We will assume that they're the same, although they're not really the same. They're only approximately the same. Okay, so I go from here, and now I do some formal manipulation. So I write this as a path integral over curves. And then here I write this into an exponential form, where this is a free energy. And again, this is not only the cost of these lines, but also has a entropic factor. So it's like you're organizing this sum into two sums. The first one is the sum over curves, and the second counts the microscopic realizations. And now, because this quantity is extensive, in the limit of large space-time scales, this you write in this way, where this is the optimal curve. So the saddle point for this quantity, in fact, the curve that minimizes this. So now, if you take the log of that, and you use now this final expression, you see that the entropy is really the free energy of this optimal curve. And now, assuming that the saddle point is actually a minimum, so it's the minimum curve that minimizes this expression. And so we need now to write who this F2 is. And here is where we now start to input some physical intuition. And so we write this F as some yeah, where this is entropy equilibrium, which in our case is the log of Q. Q is the local dimension, and would correspond to the local entropy density once you reach equilibrium. Because we said this a million times, our random unitary circuit approaches a infinite temperature state. Here we should put the entropy of the infinite temperature. So here we should have a minimum then over this expression. Okay, so here the only assumption is that this free energy you can compute locally, which is very reasonable again in a coarse-grained picture. So it means that here we can coarse-grain and look at this function here in this mesoscopic portion. Yes. Yes.
Writing the equivalent between the first line, which is that star is the same thing as the expression of the minimum.
Yeah.
We are assuming that the wave of the minimum is monovaluated, because if we were to have many minimum, then we could have a supplementary factor in front, which would totally change the scale. For example, if the minimum for gamma.
So you say here, if you have many minimum, you will have an entropic factor here.
Yes, which could modify, well, actually totally the entropy. For example, if the minimum is proportional to an exponential of t or something like this, because we have many possibilities.
Yes.
It would totally change.
Yeah. So this is. I mean, again, it's not an issue of this particular problem. So you don't so you may expect that there is some degeneracy, but you don't expect this to be exponentially large. So here, in fact, you will not have this problem. Okay. Okay. So now So now this. So let's go back again to the quantum circuit problem, and here we can actually compute this epsilon 2. And the way to do it, so we will not do it, but just to give a hint, is to compute the cost of some curve that cuts the system in half. So if this is 0 and this is x, this is 0, this is x, this is t. So you can go back to the lattice problem and count. I mean, so you can go back to the lattice problem and you can define a partition function where you have pluses here, minus here, and then you can fix the endpoint of some boundary wall, of some domain wall here. So differently, what we had before here, we have free boundary conditions, but what you can do is you take the same configuration and now you fix the endpoint of a domain wall at position x. And you do this in such a way that x over t is fixed to some value v. And now you compute the sum over all possible domain walls, where the domain wall starts here and ends here. And so this is exactly this calculation will give you exactly epsilon 2, because it counts the weight of, the cost of each domain wall, and also you sum them all. So it's the, you also count the entropy of this domain wall with this velocity v. So again, we will not do this calculation, but let me just give you the final result. So you find that Okay, so this is the result you get. So again, you go back to the lattice problem. You fix this to be x, and you take now the large xt limit in such a way that this relation is fixed and is equal to some value v. Here, you really are counting the number of domain walls associated with this curve, because in this partition function, you will count all domain walls with this macroscopic slope. And the result you get is this one, where all logs now are base q. And there is a difference if v is smaller or equal than vb, which in this case we previously computed to be this one. Okay, so now you plot this. We are taking the, we are dividing by log q, because you see that here the log q is outside of epsilon 2, right? So yes, if you don't like log base q, it's natural logarithm divided by log of q. Okay, so we plot that. And then here, this would continue to be a straight line, and here this would continue to be a straight line. This you can compute from there. You would get this to be, in this case, the purity velocity. And here, again, you can compute, and you would find, so if this is epsilon 2v, this number here would be vb. So and then you would also find, yes. So you look at that quantity that you computed analytically, and then you can infer these properties, that the value of this function in 0, it's the purity velocity. The value at the butterfly velocity is equal to the butterfly velocity, and the derivative here is equal to 1. Questions? Yeah.
The first factor is like the energy factor. The second factor is the entropy.
This one. Let's see. Yes, exactly that. Yeah. Okay, so here, this is not a theory. This is a calculation. But now this entanglement membrane theory posits that you can actually start from the same coarse grain picture, even in situations where you couldn't do this microscopic calculation. So for example, you could repeat this. You could define a similar epsilon for, say, the entanglement entropy. So S1. And now you can argue, we will not do it, but you can argue that some of these properties you need in order to have a well-defined theory. So now here, let's say we put now this epsilon of v. And you can argue that all these properties are something that would carry over also to the membrane theory of the entanglement entropy. Yes, this epsilon is sometimes called the line tension or the membrane tension because it's what governs effectively the entanglement. Yeah. Yes, so last time I was confused. So in the Q going to infinity limit, what happens is that this flattens. So it really becomes a flat line. Why? Okay, so there was a question that this is the entropy contribution, and this is the cost, the energy, and this is the entropic factor. And we showed that when Q goes to infinity, the entanglement is dominated by the cost, not the. But let me go back afterwards to the Q goes to infinity because it's going to be clear. So what I want to do now is I would like to use this theory. So we use this as an axiom, and I want to derive the consequences and see whether this makes sense. Yeah. Yes. Yes. So I think it's going to be. Let me just give you how this works, and then it will be clear what is the role of VB. So effectively, what this means, the fact that here this is a straight line, it means that effectively you can ignore whatever is here, and you can effectively chop this off and only look at what happens here. So you will never need to draw a line with this velocity. But it's going to be clear now with an example. Okay, so let's use this theory to predict the time evolution of the phenomenon entanglement entropy given an interval A. Again, we're thinking of very large A, very large T. Okay, so first let's take time which is small. So now this is T. And this is X. Okay, so one natural thing to do would be to try to divide A with these two straight lines. And the cost of this would be epsilon of 0, because the velocity of this is 0, times 2, because we have two lines. And then we have log Q. And then we have time t, right? Now epsilon 0 is here, is the velocity, so we would get that this is 2 times t times VE times log Q. So this is the prediction that we get in this case. And if t is small enough, and in particular, if t is smaller than A divided by 2V, then these are the optimal curves. So let me give an example of something which is not an optimal curve. So what happens now if I draw this with some velocity V different from 0? So the pink one now, the cost associated to this would be T. Because this is a straight line, we don't have to integrate. We can just multiply T times epsilon of V times log Q. But you see that epsilon on V is whatever V is here, it's going to be larger than V. And so this is not the optimal curve. You're going to get an energy which is larger. So this is larger than. Okay. Also, let me go back to the microscopic picture, because last time I had a question that it was a bit confusing, because when we had the microscopic picture, we saw that all the domain walls had the same weight, right? In the macroscopic picture, if you go back to that lecture, we saw that the cost really only depended on the number of time steps. So the cost of this had the same, this domain wall has the same weight of this domain wall. So it's a bit confusing. It might be confused at the beginning that this line is optimal with respect to this one. But again, because this epsilon is not just the cost, it's also the entropic contribution. And the point is that at the macroscopic level, if you draw a straight line, there are many ways in which you can realize this. But if you now have a very steep line, the number of microscopic realization is smaller, because you cannot go, to the left of this curve. This is very heuristic, but it gives you an idea of what is the meaning of this epsilon. It's the cost plus the entropic contribution. Okay, and so this is for small times. Then we take times which are larger. And now you see that we still have this possibility, but now we have a new possibility, which is this one, where the slope of this is VB. So let's compare the two possibilities. And so if you take the pink one, then you will have okay, we have to do, okay, so we do a piecewise calculation. So we first look at this piece. And so here we have epsilon of E times log of Q times, here we have delta T. And you see that, okay, let me write delta T. Yes, and then we have 2, because the cost of this is the same for the two segments. And now who is delta T? So delta T is simply A divided by 2 VB. Right, so this is just a geometric calculation that delta T is equal to A divided by 2 VB. And now we also use that epsilon VB is equal to VB. So this is now also equal to VB. So we put everything together, and here we get so number of sites times the entropy density at equilibrium. And you see that because this increases with time, there will be a time at which this is smaller than this. Yeah, and so let's see, I can. And so finally, you can write down the time evolution for the entanglement entropy. So we have a linear growth up to a time t, which is the one where this solution starts to be available. So it's A divided by 2 VB. Sorry, the 2V, yes. Okay, and so this is what we get. So there are still a few things that I have to comment, and I have. There's one detail I have overlooked on purpose. So there are still a few things I have to clarify. But if you followed me up to here, this is what you get. So at the beginning, you have some linear increase. Then you see that at one point you have to compare this with this. So once this is smaller than this, which happens exactly at this time here, then this solution becomes the correct one, and so you have saturation. Yep.
My question was, obviously it's the same cost, but if you take V to be larger than VP, since the slope is equal to 1,
yeah,
you always get the same cost function.
Yes. So this is one of the. This was exactly what I wanted to comment about. Yes. So here okay. So this is what I wanted to comment. So here I draw this line to be VB. But you see that there are. I mean, in principle, we can choose velocities which are larger than VB. So we could have also, instead of this curve, we could have picked this curve. So something with a even larger velocity. However, because this epsilon v now is a straight line, you would get the exact same result. So it's completely immaterial if you keep or not this part of the diagram, and you could erase this. Let me do this explicitly. So let me draw this with a blue line. So the entropy that you would get for the blue line would be, the same, but let's say S. Let me draw it. With a blue chalk, piece of chalk. So we'll have 2 epsilon v greater than vb times log q. And then here you will have a divided by 2 this v. Because this epsilon v now is linear vb, you see that there is a cancellation of v, and so v disappears. So you would get the exact same object. So this only works if you take v larger than vb. If you take velocity which are smaller than vb instead, because here now it's not a straight line anymore, then this you get something which is a cost which is larger. So put differently, now what you can do is you can effectively chop off this diagram, and then you say, okay, now I can only draw lines with a maximum velocity vb, and this simplifies a bit the picture. Yes?
I wanted to compute the average velocity of the trajectories of the situation around it, so the average of v square and etc.
Mm-hmm.
Then having some possibilities to go about vb would have consequences on this thermal quantity, on this average quantity, which is the velocity of the information spread.
No, but so, okay. Obviously there is a reason why VB is special, and because this is connected to the butterfly velocity. And indeed, so you can argue, these things that you also assume are true for the phenomenon entanglement entropy, one way to argue for them is precisely through causality. But then you can do this mathematical operation of summing, what I wrote there. This is well defined even if x is outside of the butterfly lat cone. So this is, if you want, it's a mathematical thing you can do. And so there is no, it's not, it's something that would make sense even if you do not have maybe this is going to be more confusing that if I don't say anything, so let me just not say anything. But you can take this as, I compute this epsilon of v by this mathematical operation. Then I get something both for v greater than vb and vb smaller than vb. I realize that because of how the theory is built, it's completely irrelevant now if I keep or not this part of the diagram. So out of simplicity, I will now restrict myself to this interval, and then I can compute the cost looking at curves with this maximum velocity vb. It's intuitive. The fact, what is intuitive is that this vb somehow has a physical meaning of maximum velocity of propagation. Namely, if you take something which is outside of this range, you're going to get something which is non-physical in a sense. Okay, so probably this also somehow answers why VB is special. Now, going back to Q goes to infinity. So for Q goes to infinity, everything flattens. So this means that there are many optimal curves. Because if epsilon v, for Q goes to infinity, you will have something where all the velocity have the same tension. So at small times, this will be an optimal curve, but also this would be an optimal curve, and so also this would be an optimal curve. Exactly because at Q goes to infinity, the only thing which matters is the cost. It's not the entropic factor. And the cost we saw, it's independent of the slope. So they all give you the same, you have to pay the same price for all these curves, and the price is exactly this, where now this VB for Q goes to infinity, it trivializes to 1. But then you still have this saturation here because this is, I mean, the cost of this is more than this. Of course, you have this flattening only here. This part continues to be what it was before. So this is also why it's less confusing to keep only this part of the diagram. Okay, so now I hope this is clear. I just want to give one final example of the theory because for one interval, it's a bit trivial, right? So we'll get something which is not mind-blowing. We just have linear increase in saturation. And in fact, if you're familiar with a different type of semi-classical theory, which is the quasi-particle theory of entanglement you have in conformal field theory, this is exactly the same prediction you get there. But now I want to give you an example where you get a different prediction, and the prediction that you get is really consistent with quantum scrambling and the fact that we have a chaotic dynamics. If there are questions, feel free to ask. Okay, so no, this is, I mean, it's complementary in that this applies to different types of systems. Okay, so the idea is you give me a Hamiltonian. Is this integrable, or maybe is this, is it true that this can be described in some way by a conformal field theory? Yes or no? If yes, then I apply the quasi-particle picture. If no, then is this a chaotic dynamics? If yes, then I expect that the entanglement follows this rule. For a bipartite, for a bipartite setting, it's immaterial which one you choose. But now the example I will show, it really makes all the difference. Okay, so now we now consider a tripartite scenario. So we have some interval here, A. Then we have some interval B here. Sorry, C. And then I call B the rest. So this is B. This is B. And this is also B. I call R the number of sites in A, which I take to be equal to the number of sites in C, which I also call R. And then I call this instance here, I call it X. And then I want to look at the mutual information dynamics between the interval A and the interval C. So this is a standard measure of quantum correlations between two intervals. And you have a definition in terms of the entanglement entropy, which is as follows. So I hope you have seen this mutual information, but if not, this is a shorthand notation for entanglement entropy of the reduced density matrix of the system A plus the entanglement entropy of the reduced density matrix over the system B. And this is AC is the reduced density matrix over the system AC. And because we are now assuming, as before, that we're studying a quantum quench, the system over the state over the whole system is a pure state. And so this is equal to SP. Because for a pure state, the entanglement is symmetric with respect to a bipartition. Okay. So let us compute now the dynamics of the mutual information using the entanglement membrane picture. Again, in the limit of large R, large X, large T, large everything. Okay. So, yeah. So, questions? Yeah. Yes. So we are studying this quench protocol, where we start from a pure state. This is a pure state over the whole system, so A, B, C. And then we imagine that we evolve the system Now, not necessarily with a quantum circuit, so it can be any type of chaotic dynamics. And so then after the evolution, we will have a pure state, sorry, a different pure state over ABC. And now there is a standard. Yes, so SAC is the reduced density matrix. I mean, it's the entanglement of the reduced density matrix over AC. And so when you have a pure state and you take a bipartition of the system, the entanglement is symmetric with respect to the bipartition. You can show this with the Schmidt decomposition over the state. Yeah. No, it's the whole thing. It's the B which is the complementary of AC. This is a standard thing. It's you use it. I mean, you use the Schmidt decomposition over the factorized space. Okay, so we now compute. We now compute the evolution of this if we do this quench. Okay. Okay, so this part we already know because we computed there. So this part is simple. SC is the same thing. So the only thing which is really non-trivial is this SAC or this SB. Okay, so first of all, let's take short times. Yeah, and let me do this calculation for R greater than X. Yeah, so we will assume R greater than X. Okay, so we take, first of all, small times. So this is A, this is C, and the rest is B. And now we want to separate B from the rest. And so if time is small, and we will quantify this, then it's easy to see that really the best thing you can do is, sorry, time should be very, very small in this picture. This is the best you can do. So 1, 2, 3, 4. This is T. And so for short times, SB of T should equal to 4 times VE times T times S. Okay, so here I'm simply counting the number of lines I draw, and then I'm using that the velocity of these lines is 0, and epsilon of 0 is V. So that's what we get. Okay, then we have a second regime where time is slightly larger. And now in this regime, you can see that the best option for you, this is B, this is B, this is B, is this one. Yeah, so now this is a different way in which you can decouple your system, where these are left as before, but now in order to isolate B, we do not draw lines anymore. We take a cusp. And now let's count where this is VB. Let's count the entropy. Let's compute SB now. So applying the steps we had before, you can see that for the regime in which this is the correct, the optimal curve, this is the entanglement. So you have X times S equilibrium. This part you get by evaluating this term as we did before, times 2 times V times S key. And then finally you have the late time situation where the optimal curve changes again. and takes this form. So now you are separating A and B by replacing this middle curve with these two cusps. And you can see that at this stage, the entanglement becomes independent of time and equal to 2 times R times equilibrium. Right, so now a little, I mean, we put everything together. We put the expression for SA, SB, and this. So one thing I have to specify is what are the exact times in which you go from one optimal solution to the other. And so you see, you can show that A holds for times smaller or equal than x divided by 2VE. B holds for okay, so this is 3 time steps. So we put everything together and we have our final result. Yes?
Maybe a trivial, but in the B regime,
Yeah.
how can we still define SA and SC since in the middle, since at the end of time, we end up with A and C to be, well, mixed up together? Can we still define a well-defined SA and SC from the formula?
So you say
Here?
here?
Yes.
How can...
A and C are mixing up.
I don't know, but no, but this is a picture. I mean, this is a geometrical picture. It's not like now you're blending together regions A and B, right? At every time step, you still have a pure state. You still have a well-defined definition. Now, I mean, this is a semi-classical picture in which you want to draw lines in order to separate B from the rest, right? So here, B is this.
For this, I agree, but I
Yeah.
know how you compute the I of AC is S8 as C minus S of B. So B is still very well defined.
Yeah.
But A and C are no longer defined.
No, they are always well defined. A and C.
Oh, okay.
I mean, there are always intervals in your system size. Yeah, there's no issue. The fact that now in this picture they seem to be blended together, it's really just this picture, but they continue to be well defined. Maybe, yeah. Yeah, sure. So,
I think it would probably make sense when you write up the expression for SA of T in the
right, and so this is defined at all times, right, the state. The trace over BC is always defined at all times, and so SA. So there's no issue. This is defined at all times. It's okay. Okay, so here we put okay, so So this is what you get. The first interval would correspond to regime A. This is regime B. This is regime C. And so you see that you get a three-step object for the mutual information. Again, I didn't insist too much on the precise scaling limit because I didn't want to make things too cumbersome. But you see that there are cusps here. This is claimed to be the exact result you would get for a chaotic dynamics in the scaling limit, which is a very precise definition, where you should take the subsystem sizes to infinity while keeping all the ratios constant. Yeah. Yeah, sorry. This is the slope is the same. It's just I suck at drawing. It's the same, and it's equal to. So let me put formulas. So A, this is region A, and it's equal to 0. Then we have region B. We call this region 1, region 2, region 3, and region 4. Let me divide by S equilibrium. 2 times TVE minus X. All right, so now, I mean, we have 30 minutes, but I want to give a toy introduction to this dual unitary circuits. Again, if you're interested, we can discuss this at some other time. So now, there are many ways in which you can change or extend or modify this random unitary circuit, perhaps adding some structure, so some maybe U1 charge, this has been done, or maybe taking long-range models for the circuit, so you give up the local structure. But then there are also very useful models where you do not have disorder. And so the model that I will introduce now, in fact, is usually taken to be a translation invariant model. And this has some advantage. It could be, for example, at the level of actual implementation of quantum devices, because you want to implement one single gate and repeat that. And also, it captures more closely the idea of quenches in translation invariant Hamiltonians. So I just wanted to now give an idea of the kind of additional techniques that you can have in studying these models, and how, again, the quantum circuit structure, even in this case where you have no disorder and so a priori no simplification, can still give you indeed some simplification and some new technique. So we now take a translation invariant quantum circuit. Okay, so now so this I will draw for time equal to 3. So now these operators are all the same unitaries, which I call V. And you see now that this time evolution operator as a natural invariance under translation of two sites. So if we want to mimic some quench over some translation invariant system, then the idea is we, instead of taking translation invariant states, we take two-site translation invariant states. And so the simplest thing you can do is to start with some, say, product states which respect this two-site translation invariance. Right? So in formulas, we have some initial state. on a system of L site. Yeah.
Translation is varies solely from the rate, solely from the state with 512 equals 524, or also the blocks that you put inside your system.
The blocks, you mean? Yeah. Exactly. So they are all identical. I want to enforce now translation symmetry, and now not only they are identical, they're not random. So they are fixed. So you decide what they are. And this type of architecture, for example, you get when you do tractorization of local Hamiltonian dynamics, right? So in that case, they are all the same. So now the difference will be that we will, I mean, with respect to tractorized dynamics, we don't choose them to be some short time evolution of some local Hamiltonian, but in principle, they can be something different. And so the game is to choose them to, in such a way that they are simple enough that we can still solve the dynamics. Okay, so now, because there is the, right, and then we have our evolution operator, which is, again, some U. Okay, now, so one of the things which is difficult, so one of the reasons why it's difficult to simulate classically the quantum dynamics is, again, entanglement. And this, you can see this in a very transparent way if you try to simulate the dynamics using tensor network algorithms. So this is a set of techniques where you can go quite far, for example, in the number of qubits, so you can simulate very large system sizes. But this kind of methods really breaks down whenever the bipartite entanglement in your system grows too much. And we saw with the previous models that we should expect this kind of this bipartite entanglement to really grow linearly with the system size. So this means that even with state-of-the-art tensor network methods, you have some effective cutoff in the time you can classically simulate your system. But then I mean, in the quantum circuit model drawn here makes it very natural to try to get around this problem with a technique which is called the space-time rotated approach to the dynamics. So this appeared in the recent literature, again in the tensor network literature, in the group by the Syrax group. So to 2009, so quite an old idea, but recently it was realized that this idea and very closely related ones really shine in the quantum circuit setting. So, okay, so let me try to explain how this works. And we do this in the simplest setting where we imagine we want to compute the time evolution of some local operator. Right, so AX is some operator localized at some position X. For example, we can take qubits, and this AX can be some Pauli matrix localized at X. Here, because the dynamics is non-random, we don't have the issues we had before, and so this is it's really the physical interesting quantity we want to look, for example, after a quench. Okay, so now there's no disorder, but it's still convenient to look at the dynamics in the folded picture, because now we have one U and one U dagger. This would be a two replica folded picture. So again, we use this notation where this is V and this is V star. It's this two-side gate. And also we introduce the folded initial state. Yeah. So here we use the same graphical notation we have used throughout the course. So this we initially write, as a tensor network, and then we literally fold it. And so in the folded picture, this is what we get. Now we are not taking averages. So this is just a superposition of two gates. And also here, this circles with the same notation we used before. It's a maximally entangled state between the two replicas. And AX is the same thing, but we put a operator in the middle. Okay. So now the idea is we look at this, we stare at this long enough, and then we realize that it's not necessarily true that we need to look at this as a dynamics in this direction, but we now wish to exchange space-time and look at this as a dynamics in the other direction. So this could seem like a silly idea, but there is this. The motivation for this is that whereas there are theorems and reasons why the entanglement should always grow when we look at the dynamics in this direction, a priori there's no reason why entanglement should grow in the other direction. So if we're lucky, then maybe we can engineer the gates in such a way that the dynamics in the other direction does not grow. I will make this precise. And so maybe the rotated dynamics then can be simulated efficiently at the classical level. So this is the idea, but now we introduce some formulas. And so we now break this down into more elementary terms. And so we define the transfer matrix E to be this geometrical object. Okay, so we have this transfer matrix, which it's a slice of this picture. That is for t equal to 4. Here, this was for t equal to 3. So it's a slice of this. And this is a transfer matrix where you have, in this case, 4 input, and you have 4 output. So this is t. So this is a transfer matrix in the space direction. It takes as an input some time Hilbert space and spits as an output at state in that same Hilbert space. And then we also introduced a similar object, but we're here, instead of closing with this maximum entangled state, we close the diagram with A. So it's the same thing, but here we put A of x instead of closing with a circle. Okay, so after introducing this, we can rewrite the expectation value of interest in this way. So here we are assuming periodic boundary conditions. And the claim is that you can view this contracted tensor network in this way. So you have application of L minus 2. L is the system size. And what we do here is we apply many of these rotated transfer matrices. Then we hit this slice where you have A of x. And then we have L divided by 2 minus 1 transfer matrices. Okay, so for the moment, we did nothing. This is just a rewriting of the same thing. But then we analyze what this transfer matrix is. And you can prove that E. So in general, E is not a Hermitian. However, you can prove that there is a, all right, okay, so what you can prove is that all eigenvalues of E are 0. So these are the eigenvalues. When I say eigenvalues, I mean the eigenvalues which appear in the Jordan form of the matrix, except for. So you can prove that all eigenvalues of E are 0, except for one of them, which is exactly equal to 1, which has geometric and algebraic multiplicity equal to 1. And so this means that there is a right and a left eigenvalues of E, such that so I am a bit rushing, so I don't have time to prove this. But you see that if you accept this, then when you expand this to the power of L, if L is large enough, then this will project onto the left and right eigenvectors. And okay, so okay, and here also without loss of generality, we can assume that the two are normalized to 1. Okay, so we plug in this information into the original expectation value. And letting L goes to infinity. So we're computing this thing in the thermodynamic limit. Then this becomes okay, so we let L goes to infinity. We end up with this expression. So a sandwich of the transfer matrix E with respect to the left and right leading eigenstates of the transfer matrix. And so graphically, we collapse the infinite diagram onto this object here. Yeah. Yes, so indeed, we don't need L to be infinity, we need L to be large enough. In principle, you should say, well, but if all the eigenvalues are 0, isn't it enough to have just one application of E? But the point is that these eigenvalues are 0, but they have non-trivial Jordan blocks. So you need to apply a few times in order to kill those blocks and get a... Okay, so this is what you get. But this is very simple to prove. I just don't have the time. I could do half of the things I wanted to do in this course. Yeah. Yes, I will. So, exactly. So how should we interpret this now? And you see that even intuitively, so here we're saying that the dynamics of this local bit of the system is now determined by some left and right objects which really encode how the system acts on its own subsystems. So they really encode the subsystem system behavior. So in a sense, we can say that L and R are so encode. Sorry. Yeah. So we can, in a very not precise way, but this left and right, they encode how the subsystems interact with the rest of the system. And in a sense, this subsystem-system interaction mimics the one of a thermal bath with respect to some open system dynamics. Right. So this type of so this approach tells us that if we want to solve the dynamics of some local subsystems, then we don't need to really compute the state at each time step, and this would be hard/impossible to do even with tensor network methods because of this entanglement barrier. But we really not just need to compute this left and right fixed points. And of course, then, I mean, there's no free lunch, so typically we would expect that getting these objects, then it's the hard thing. Okay, however, the question then is it maybe possible that there are some special dynamics for which this left and right are simple, where simple, let's say one would expect simple to mean, for example, not a lot of structure or maybe some small entanglement, some matrix product state form. And the answer is yes, they exist. They are non-trivial. And so at the moment, some families of these circuits exist. And dual unitary circuits are the simplest family, where this left and right baths are exactly product states. So they're stupidly simple. And so for dual unitary circuits, okay, now I have to make some remarks. Okay, so first of all, dual unitary circuits, I will just give the definition now, and then perhaps we will stop. But they were introduced by Bruno Bertini, Thomas Brosen, and Pavel Koch in this paper. Okay. Then I also wanted to say that this idea of interpreting this fixed point of these transfer matrices in a physical sense was recently expanded upon by the group of Abanin. So where this left and right fixed points were called influence matrices. Making contact with some object which was originally introduced by Feynman in the context of open system dynamics. Right? And also, I wanted to stress that here I'm not being completely precise because the statement also depends on the initial states. So this it's true for certain families of initial states. And so this you can find in our paper. And also, this was recently, I mean, for more general discussion, you can also look at paper by Alessandro in the audience and Bruno. Okay. Okay, so now in the last 5 minutes, let me just give the definition of the circuits and then simply mention a few of their properties, and unfortunately we'll not have time to study them in more detail. Okay, so yes. Okay, so definition. Okay, so given the gate V, we define the dual gate from, so we define it in coordinates as follows. Okay, and so we say that V is dual unitary. if it's unitary, and so v dagger v equal identity, but also if its dual is unitary. So
What is going to be used in the zero? Our second one, is it a V or is it a V?
this,
No, just about in the formula.
it's a v, sorry. Yes, let me just to check that there are no typos. Yes, it's correct. Okay. Yes. So let me make sense of this definition. So it's useful to look at this definition graphically. So the first one is just unitarity. So if I have v dagger here, then I have e here. This is the unitary condition. And the dual unitarity condition instead is so it's the dual unitary condition states that the subject remains unitary even if you look at it as a object where this is the input and this is the output. So this is why dual, because this is it would correspond to the space-time rotated picture. And also, these expressions are very naturally converted to the folded picture. No, if I define now, so in our notation, if you fold this, you get this, and so this. So the dual unitarity means that this is equal to simply this. In this condition instead, okay, so it's a special family of gates with an additional unitarity property. And this is the definition. So then you can dual unitary gates, all the gates that satisfy this. And then the question is, can we parameterize them? So the problem of parameterizing them in arbitrary dimension, it's an open problem. But this has been solved, again, by Bertini and collaborators for qubits. And so let me give you the parameterization there. So we look at these guys and see that they're non-trivial. So let me now switch to letter U to indicate the gate. Okay. Yes, okay, so this is the parameterization. Phi is just a phase, which is in fact irrelevant. These are single site unitaries, which can be whatever. So whatever choice you make for them, this is still going to be dual unitary. And Vj is the non-trivial, the structure a bit of the gate, which is written here, where sigma x, y, and z are the Pauli matrices. And this is parameterized now by some real parameter here. Okay, so I want to just say a few things. The first one is that this gate is non-integrable. So for generic choices of U and V, this is not Yang-Baxter integrable, has no conservation laws. And in fact, it exhibits chaotic properties as we have quantified them. So to make this more precise, you can, yes, you can, I mean, right, so sorry, 1 second. Okay, so this is non-integral, so for generic choices of the parameters, this is chaotic, and in fact, up to a measure 0 set of this family, the dynamics, the translation invariant dynamics that you get is going to be maximally chaotic in a way that now we'll explain. But there are some integrable families. In particular, so if you take now U plus minus equal V plus minus equal the identity, then the model becomes Yang-Baxter integrable. And it becomes a special line of the characterized XXZ Hamiltonian. But away from this point and up to a 0 measure of the space of parameters, then you get something chaotic. So when I mean chaotic, I mean that you can compute different probes of quantum chaos. There is one in particular which relates to what we have computed, which is OTOCs. So you can find a discussion, I mean, a computation of OTOCs for this model in this paper. And OTOCs is one of the probes that tell you really that these are chaotic dynamics. So if you take the results of this paper, you would find that the OTOC for generic dual unitary circuit would have this form. This is 1, so it's the same that we found for random dynamics. But now we see that there is no broadening of the Lycon. So for dual unitary circuits, we have that VB is equal to 1. And in fact, VE is equal to 1. Sorry, to 1. So you remember in the previous case we found that the butterfly velocity was q squared minus 1 divided by q squared plus 1. Here the butterfly velocity is 1, is as large as possible in the quantum circuit geometry, and it's also equal to VE. So for dual unitary circuits, you will find that the membrane theory epsilon V is in fact a flat curve, which is the same as the q equal to infinity limit for random unitary circuits. Okay, so here, I mean, I'm going to stop. I just wanted to, again, stress that this is a family of non-random circuits which has chaotic properties, and still you can do some analytic calculations. And this, even traditionally, it's a big deal because people, for a long time in the dynamical contexts, associated solvability to integrability, in particular to Yang-Baxter integrability. And this is a family of circuits where you don't have conservation laws, you don't have integrability, and yet you are able to do analytic calculations even at the microscopic level. The type of things you can compute analytically, it's, for instance, 1-point correlation functions or 2-point correlation functions. And this is related to the fact that these left-right objects that we introduced are product states. But you can also compute analytically entanglement dynamics or more complicated things like OTOCs, etc. And so with this, I conclude. Yeah, please.
In So this limit method is fairly easy because when you take the limit of large L of large system, then you will have no problem to compute this. But if, for example, you have two operators, A and B, that you were trying to compute before, which are distant from each other, in the limit of a very large distance, then you can just apply the same trick and say right left, basically.
Yeah.
But if you are not in this limit, what you have to extend the central operator to some limit where the limit will be quite large depending on the distance between the two operators.
Yes. Okay. So this formalism in general, indeed, it might be challenging if you want to compute two-point correlation functions, as you said. Then in practice, you can still do it at some computational cost. But for dual unitary circuits, in fact, you can go beyond and get two-point functions even analytically, exploiting some further properties of dual unitary circuits. One thing I wanted to stress, however, is that in the traditional setting, even computing one-point functions, it's very complicated. Typically, when people study, do numerics to maybe probe thermalization dynamics, maybe you want to test the GG hypothesis or whatever. So you compute time evolution of some local observable. You start from some number. This starts to oscillate, but then you have to stop the simulation at some point. So it's really difficult. Even with state-of-the-art numerics can be very difficult. So this is a way to get around that problem. And sometimes this works very well. Sometimes, it doesn't always work, of course.
I still don't understand this eigenvalue statement and what it has to do with the system acting as
No. So let's say the eigenvalues are, sorry. No, okay. So the eigenvalues, I would say it's just a technical condition. It just, you can understand this by, okay. So the only physical lesson you learn from the statement on the eigenvalues is that you can apply the transfer matrix a sufficient number of times, and after that, this will converge towards some fixed point. Okay, so it allows you to replace the infinite system size with the left eigenstate. So it effectively allows you to replace the effect of the rest of the system with some, right? Because because they are all zero except for one, it means that you have your large system size, you focus on the slice. In principle, you should keep into account all the left part of this. But because all the eigenvalues are zero except for one, if you apply this transfer matrix sufficiently many times, then you can replace all this infinite thing with just this left bath. No. This is completely general. You can prove it in completely general way. It just follows from unitary. So you just assume that your V are unitaries. Yeah, maybe we can do that proof later. It's a one-line proof. It's not difficult.
It seems like yes, there's small eigenvalues. The system thermalizes itself.
Yes, not necessarily. So this does not imply thermalization, right? Because this implies that you can encode the interaction system. So this is why I had quotes, right? So this tells you that you can encode the subsystem system thermalization into two guys, left and right. But then in principle, if left and right are maybe strange or pathological, this interaction can lead to some, something which keeps oscillating, it doesn't thermalizes, and etc. So this does not immediately imply thermalization. This really only tells you that you can encode the subsystem interaction into some well-defined object, which may or may not be simple, which may or may not lead to thermalization. This is what in Van In's group they call influence matrix. It's this object here.